Hi everybody, welcome to another video in linear algebra, section 6.4, the Gram-Schmidt process. The Gram-Schmidt process is a simple algorithm for producing an orthogonal or orthonormal basis for any non-zero subspace of Rn. So let's say we have just a basis. The vectors may or may not be orthogonal. This process will help us to produce an orthonormal or orthogonal basis for the same subspace Rn. The process, even though we say simple, the concept is simple. However, when we have a lot of vectors, this will get a lot more complicated later. And usually, when we have a computer programming or something, that will be easier. If we do this by hand, we can only do the demonstration of a few simple examples. We cannot get too complicated in the computation. Right. So the idea is we just have two random vector. Let's say x1 and x2. Right. So this process is saying that the first step is we're going to let v1 to be the same as x1. Right. So now we turn that the same vector is going to be v1, the first vector in the orthogonal basis. And then we find the projection of x2. So we're just going to move that here. Okay, about right. And the projection. So this is going to be the projection of x2 onto v1. And then we subtract v2. v2 is equal to x2, subtract that. So pretty much after this process, we're going to get this vector here. So we find orthogonal projection, and then we subtract from x2. So the idea here is to get this vector, and because that vector is orthogonal to v1, so we're going to let this equal to v2. And if we have v3, we find orthogonal projection onto these two vectors, and we subtract that, we have the third vector will be here. So v1, v2, and then v3. And then of course, if we have more and more vectors, we can just keep generating. After we do this, we have orthogonal basis for the same subspace of Rn. So let's look at this example. Let W be spanned by x1 and x2, where x1 is that and x2 is that. Construct orthonormal basis. So this is orthogonal, and we have to normalize the vectors in the basis. Right, so the process says that we just let v to be the first vector. So the first step, we let v1 equal to x1. So that's easy, right? Just say 3, 6, and 0. And then next, to get to v2, it's going to be x2, subtract the projection of x2 onto v1. Yeah, so that's exactly what we do here. So x2 is 1, 2, 2, and then subtract a projection of x2 on v1 is x2 dot v1, v1 dot v1, v1. So we have 1, 2, and 2. x2, 1, 2, and 2. Dot v1, 3, 6, 0. And then over v1 dot v1. Yeah, when there's only two vectors, that's easy, but when we have more and more vectors, the process will be more and more complicated. It's more suitable to do it with a computer than to do it by hand. But when we have the orthogonal basis, do have some nice properties that we can use. Then the computation will be a lot easier if we would do it with original basis. So between 2 times 6, 12, 2 times 0, 3 times 3 is 9, 36, 0, 3, 6, and 0. So we have 1, 2, and 2. Subtract, that gives us 15 over 45. 15 over 45 is 1/3. 3, 6, 0. So that gives us 1, 2, and 2. Subtract 1, 2, and 0. Yeah, 1/3 multiplied to that. And we have 0, 0, and 2. Right. So we have V1, we have V2. So we said orthogonal basis is going to be the vector 3, 6, 0 and 0, 0, 2. Of course, we can also write vector in column like 3, 6, and 0 and 0, 0, 2. Now, if we want to turn this into orthonormal basis, we have to normalize. So we have normalize V1. So we have U1 is the unit vector in the direction of V1. So just V1 divided by magnitude of V1. 3, 6, 0 square root of 3 square, 6 square, 0 square, and that's just 3, 6, 0 square root of 9 plus 36, 45. So we have 3 over square root of 45, 6 over square root of 45, and then 0 divided by anything, 0. So we normalize V1, and then we normalize V2. So U2, V2, V2, right, V2 just 0, 0, 1, 0, 0, 2, sorry. And then we divide by the magnitude. So we have 0, 0, and 2. That's square root of 4, which is 2. So that gives us 0, 0, and 1. And so when we combine these two together, the orthonormal basis for W I run out of space, so I cannot write as a column vector. So I'm just going to say, if I want to write as a vector, we can just say 3 over square root of 45, 6 over square 45, 0 transpose, and then 0, 0, 1 transpose. We can write that as a vector, or like that, or just that notation. Right, when we have two vectors, that should be easy. Right, now when we have three vectors, that will be a slightly more complicated computation. But now let's say we have x1, x2, and x3. First, we're going to show that they are linearly independent, because if they're not linearly independent, then we'll just take one of them out from the basis. So in that case, we only have two vectors left, right? So if they are linearly dependent, meaning one of them depends on the other two, so that's, we don't need the last one in that case, and we have two vectors. That would be easy, right? So how do we show that the vectors are linearly independent? Well, it is linearly independent if the linear combination that produce 0 is going to be so in that case we only have trivial solution. Actually, I still have this case here. So linearly independent, that is where we have only trivial solution. That means no free variable. Right. So in that case, we're going to say linearly independent is equivalent to the system x1, x2, and x3. This is the homogeneous system, right? Equal to 0. And that equation in the augmented form here has has only trivial solution. That means no free variable. So we're just going to do that. So this homogeneous system has only trivial solution, meaning no free variable. So we're just going to put x1, x2, x3 reduce row echelon form. We might need to add an extra row of 0 into it because otherwise, for some weird reason, it will not do reduce row echelon of 3 by 4. I mean, when we have more columns and we have more rows than columns. So in that case, it's just 4 by 4. Right. So we're going to add 0 on the last column. Right. 1, 1, 1, 1. 1, 1, 1. Right, so we do that, and that's what we have. So here we have the pivot here, here, and here. So no free variable. If there's no free variable, that means it's only trivial solution. Right? So no free variable, so we cannot have infinitely many solutions. In that case, we only have trivial solution, and because of that, the set of the vectors are linearly independent. Meaning that the basis has 3 vectors, meaning that we're going to find 3 vectors that are orthogonal to each other to be the basis for W. So that is the Gram-Schmidt process. So first, V1 is equal to X1. Once again, I'm going to write this in vector in this form to self space. Right. Next, to get to V2, it's going to be X2 subtract the projection of X2 onto V1. Right. X2 0, 1, 1, 1 subtract projection of X2 to V2 is X2 dot V2 right. So 0, 1, 1, 1 subtract X2 0, 1, 1, 1 dot V2 sorry, v1. We don't have v2 yet. Right, v1 is 1 1 1 1. The numbers here is very simple already, so the calculation is not that bad. And I said this process is more suitable to do it with a computer program than to do it by hand. So 1 1 1 1 times that, so we have 0 plus 1, so there will be 3 on the top, and then 4 at the bottom. So we have 0 1 1 1, subtract 3/4 3/4 3/4 and 3/4. So that will be negative 3/4, and then 3/4 3/4 3/4. That is v2. I'm sorry, 1 minus 3/4 is 1/4. So this is v2. Now we go to v3. v3 will be from x3, subtract the projection of x3 onto v1 and v2. So that's why this will get more complicated as we go in more and more vectors. Yeah, so this is a very simple example and we'll take the whole page already. So x3 0 0 1 1. Projection of, just going to say this, 0 0 1 1, subtract projection of x3 to x1, so x3 to v1, sorry, v1 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 v1, subtract x3 v2 v2 dot v2 v2. Right, 0 0 1 1 v1 1 1 1 1 and then x3 0 0 1 1 v2 negative 3/4 1/4 1/4 1/4. As you see, it gets more and more complicated. And then because we multiply by v2, which is negative 3/4 1/4 1/4 1/4. You see, only 3 vectors and we run out of space already. So try to write small. Right, 0 0 1 and 1, subtract. Right, so at the bottom that will be 4 at the bottom. That's easy. And then the top 0 0 1 1, so just 2 on the top. Right, 0 0, 1/4 and 1/4. 1/4 plus 1/4 is 1/2. Then the bottom. Right. Three, 4. I just want to say 3/4 negative, but we multiply by itself, so that's just square, and plus 1/4 square, and we have 3 of those. Oh, it's just 3/4. It's not that bad. So that would be 0, 0, 1, 1, 1/2, 1, 1, 1, 1, 1/2 divided by 3/4. That's 2/3. Right, just going to put in the calculator here. Right, 1, 1, 1, 1. Subtract 1/2. 1, sorry. 0, 0, 1, 1, negative 0.5, 1, 1, 1, 1, right? Minus 2/3. 2/3 times negative 3/4. I could enter just negative 0.75. 3/4, and then a quarter, 1/4, 1/4, and 1/4. Close curly bracket. Right. Then the fraction 0, negative 2/3, 1/3, and 1/3. Right. So we have 3 vectors. V3, V2, and V1. So we said, W equal to the span of those 3 vectors. And this vector, of course, are orthogonal to each other. One, 1, 1. V2, negative 3/4, 1/4, 1/4, 1/4. 0, negative 2/3, 1/3, and 1/3. Yeah. So that is the Gram-Schmidt process, and we use that to find orthogonal basis for only 3 vectors. That's some work already. Right. Now, why do we need that? If we have an n by n matrix has linearly independent columns x1 to xn, then applying the Gram-Schmidt process with normalization, so we have x1 to xn amount to factoring 8. So this will be a vector x1 to xn. This factorization is widely used in computer algorithm for computation, of course finding eigenvalues and all other things. But like that, it is a lot more suitable to to use on a computer than to write by hand, because you see when we get the computation we have square root and all kind of that. If we do it by hand, in the calculator we just use the approximation and we just have decimal number, so it's easy to keep track on the computer. So once again, we have the matrix A with linearly independent column. We can turn that into the factorization into QR form. Q is an is the matrix of orthonormal basis for column A, and R is the n by n upper triangular matrix with positive entry. Right, now let's find the QR factorization of A for that. So we did this earlier and we found the orthogonal basis for that, those three columns. Now, in order to find the QR factorization, first we have to normalize the vectors. So we have everything in the length equal to 1, and then that gives us the vector, the matrix Q, and then we can get the matrix R from that. So like that, sounds simple. Right, first let's just write from what we have from the previous example. We have the vectors v1 1 1 1 1, v2 -3/4, 1/4, 1/4, and 1/4, and v3 0, -2/3, 1/3, and 1/3. Yeah. So we have those three vectors which are orthogonal to each other. Now to normalize it, because that takes too much space already, just say actually I'm just going to say normalize v1, meaning finding the vector that is in the direction of v1 but the length equal to 1. Right, so v1 1 1 1 1 was square root of the sum of the square of the component. So that 4, square root of 4 is 2, so we just have 1 1 1 1 over 2. So 1/2, 1/2, 1/2, and 1/2. And next, normalize v2. Which is finding the vector in the direction of v2 but the length equal to 1. Right, so that vector. Now it is more complicated. -3/4, 1/4, 1/4, and 1/4. Square root of the square Right, so the vector is still just that. I think we did the denominator. Where was that? Oh, here. Yeah. Right, 0.75, which is square root of 3/4. Which give us the vector v2. I'll just write. So square root of the top, square root of bottom, so square root of 3/2. Multiply reciprocal, meaning 2 over square root of 3. Right, multiply inside, have negative 3/2 square root of 3. And then 2, and for that cancel, we have 1/2 square root of 3. Right. So that is v2. And normal line v3 u3 equal v3 over normal v3. Right. 0, negative 2/3, 1/3, 1/3. Right. So as to the inside the square root, we have 2/3 square, 1/3 square, and then 2 of them. Which is 2/3. Multiply reciprocal, square root of 2 over square root of 3. So I'm going to flip that. Right. Yeah, just square root 2 square root of 3, and then multiply reciprocal, divide fraction, so we're going to flip. And then multiply inside, that will be 0. Negative 2 square root of 3 over 3 square root of 2. It's not particular. Simple. Square root of 3 over 3 square root of 2, and square root of 3 over 3 square root of 2. Right, so we normalized the vectors. Now we're going to stack that into the columns, and we'll have vector Q, and then we can get vector R from it. So we have Q, it's just going to be the columns. So we have Q, matrix whose columns is orthonormal basis. So we just have this in column. One half, one half, one half, and one half. Just going to write vector Q. Normalize of V2. it's going to be that -3 to square root of 3 1 to square root of 3 1 over 2 square root of 3 and then v3 normalize of v3 0 -2 square -2 square root of 3 over 3 square root of 2 square root of 3 3 square root of 2 square of 3 3 square root of 2. So that is Q. And then A equal to QR. So we can say R is equal to Q inverse times okay. Notice that Q does not have an inverse because it is not a square matrix. So in that case, to find R, we cannot take Q inverse because it doesn't exist. But the nice thing about this is it's going to be Q transpose A. Right. And I'm not going to calculate that for one reason is we run out of space, and that's just a bunch of square root. Just multiply. It's not that difficult. Right. Probably we'll do that in the next example. Right. Like I said, this is a lot more suitable to use this on the computer than to do it by hand. Right. Let's say we have those vectors. Construct an orthonormal basis for factorization and then factorization for A. Right, so this one we're going to do that by hand because that looks simple enough. Right, so we have x1 and x2, and they are linearly independent because they are not multiple of each other. So first find the orthogonal basis. Find orthogonal basis using the Gram-Schmidt process. Using the Gram-Schmidt process. V1 equal to x1 0, 4, 2. V2 is x2 minus projection. This one look like a dash. Subtract projection of x2 onto v1. So 0, 4, 2. That is x2, sorry. Five, 6, -7. Subtract projection of x2 onto v1. So x2 onto v1. Right. Five, 6 minus 7. V1 0, 4, 2. Where's the calculator? Oh. Right, that will be 0, 24, 6 and 4 minus 14. The bottom is 0, 4, 4, that's 16. 2 is 4. Oh, it's not that bad. 5, 6, negative 7, subtract. That's 10 over 20, so 1/2. So that gives us 5, 6, negative 7, subtract 0, 2, and 1. So 5, 4, and negative 8. Right. So that we find a orthogonal basis for W. Now we normalize this. Right, so we have U1 is V1 over magnitude of V1. So for 2, so square, 4 square, and 2 square. So that gives us 0, 4, 2 square root of 20. So we have 0, 4 over square root of 20. And 2 over square root of 20. Square of 20 is 2 square root of 5. 4 times 5, which is 2 square root of 5. Right. So substitute that in here. So that would be 0, 2 square root of 5, 2 and 2 cancel out. So we just have 2 over square root of 5. And then 2 square root of 5, 2 and 2 cancel out. We have 1 over square root of 5. Right, U2 is V2 over norm of V2. So V2 is that vector and we have 5 square, 4 square, and negative 8 square. $105. Let's see, it's divisible by 3 and 5 and 7, so we cannot reduce anything like what we did here. Of course, when we put them together, we have the vector Q in column 0, 2 square root of 5, 1/5, 1 over square root of 5, 5 square of 1 over 5, 4 square of 1 over 5, and negative 8 square of 1 over 5. So that vector Q. And factorization is A equal to QR. So R is equal to Q transpose or Q transpose A, sorry. So next we're going to do Q transpose A. Right, Q transpose Q inverse times A. The vector A got just composed of two vector x1 and x2. x1 0, 4, 2 and x2 5, 6, negative 7. Right. So 2 by 3 and 3 by 2. So we end up going to be a 2 by 2 matrix. Right. 0 times 0. 4, that a square root of 5 plus 2 square root of 5. That's the 10 square root of 5. And then 0, 12 square root of 5 minus 7 square root of 5. Right. Next, 0, 16 over square root of 105. And so 0, 16 1 square root of 105 minus 16 right. Of course, like what we have earlier, we say that where R is an upper triangular matrix with positive entry, so that's why this is supposed to be 0, right? So it will be upper triangular. And then the last one, 5 square root of 5 times 5, 25 square root of 105, 24 square root of 105, and 56 square root of 105. That gives us the matrix R 10 over square root of 5 and then 5 over square root of 5. 0 is 25, 24, and 56. And 5. Right, so that is the matrix R. So it takes a lot of work even for the very simple example already. But in terms of uses, if you put this in computer program, when we have 100 vectors with a lot higher dimension, this is a very simple process for computer. But the Gram-Schmidt process gives us the orthogonal basis. Normalize the vector give us the orthonormal basis, which put together in the vector Q, and then we can find R equal to Q transpose A, and that's what we have. So that's all I want to cover in this section. As always, thank you for watching and see you in another video in linear algebra.